In this video, we're going to look at the second major class of problems in quantitative analysis, and these are called volumetric analysis problems. But really what this is stoichiometry with solutions. So now we're going to be using the molarity and the concentration and volume of solutions as a new input into our stoichiometry workflow. Let's take a look at what volumetric analysis really is. What this basically means is this is the volume of a solution that is required to react with another reagent. So in essence, this would be like saying, if you have 5 grams of one reagent, how many milliliters of a given solution of another reagent would you need if this is the concentration in order to react with that 5 grams? And so you could see the setup here being either a limiting reagent type problem setup, or you could see this being set up as simply just going from one reagent to another. You should be kind of thinking here limiting reagents, percent yield. All of these concepts can come back, and we're going to show you how to deal with the molarity and the volume as an input into our mole calculator. But once you get to the number of moles, you can do any one of the types of problems that we had in chapter 3: limiting reagent, percent yield, actual yield, all that stuff. So just keep in mind we have this flow chart, right? So we have moles, and we can go to mass using the molecular weight, grams per mole. And we can go to the number of things, number of particles or whatever you want, using Avogadro's number. And we added a new entry into the mole, which was if we have volume of a solution, we can use the molarity as a unit conversion that allows us to get to the number of moles. And once we're in the number of moles, we can then get to the number of moles of any other reagent in a balanced reaction using the mole ratio, and then for moles of B we can get to the mass, the number of particles, or the molarity. So the fact that the molarity can be used as a unit conversion to get to moles from the volume of the solution means that it inputs into all of the things we were doing in chapter 3. So let's take a look at an example problem. In lecture problem 4, it says, how many mils of a 0.375 molar nickel sulfate solution would be necessary to react with 45.7 mils of a 0.265 molar sodium phosphate solution? And we have a balanced reaction. So this is what I'm getting at with going from moles of one thing to moles of another. So in essence, what we have to do is we have to get to the number of moles of sodium phosphate, because that's what we get information on. This is our starting point. And then for moles of sodium phosphate, we have to get to moles of the nickel sulfate. And so to get to moles of the sodium phosphate, we're going to take the volume that's given, and we're going to use the concentration. That's going to be our unit conversion to get us to moles. Once we have the moles, we can use our mole to mole ratio, and then finally we can get back out to the volume that we need using the concentration of the nickel sulfate solution. So this is what we mean by using solutions in stoichiometry. So let's start the problem with what we have. So we have 45.7 mils of sodium phosphate solution. Now, we know that because our concentrations are in molar, the units of this are in moles per liter. So we have to convert to liters, unless we're doing a dilution problem. That's the only problem where you don't have to do that. In this problem, this is not a dilution problem, because we're not simply adding water and making it a little less concentrated. We are looking at a reaction. So we have to get to liters. And to do that, we're going to say for every 1,000 milliliters, there is 1 liter of the sodium phosphate solution. That just gets us into liters. Now, to go from the volume into the moles, we have to use the concentration. And really, what this concentration is saying is that we have 0.265 moles of the sodium phosphate in every 1 liter of solution. So we can set that up. So for every 1 liter of solution, we have 0.265 moles of sodium phosphate. Now, once we're in moles, we can go from moles of sodium phosphate to moles of the nickel sulfate, and we're going to use the mole-to-mole ratio. So for every 2 moles of the sodium phosphate, and I get that from the coefficient, we have 3 moles of the nickel sulfate. Now, once we have moles of nickel sulfate, we can go to the volume using the concentration. So what this concentration tells us is that we have 0.375 moles of nickel sulfate for every 1 liter of nickel sulfate solution. So we have 0.375 moles of nickel sulfate for every 1 liter. And then because this problem asks us for the milliliters, we have to convert to milliliters. So for every 1 liter, we have 1,000 milliliters. So when you plug this into your calculator and you do 45.7 times 0.265 times 3 times 1,000, and then divide by 1,000, divide by 2, and then divide by 0.375, you get a grand total of 48.4 mils of that nickel sulfate solution. So that shows you how you can use the concentrations to feed into your mole ratios. Now, for example, if you wanted to do a limiting reagent problem, you could easily do that with this problem. Let's say that we gave you volumes and concentrations for both nickel sulfate and sodium phosphate. Well, what you would do is you would come up with a number of moles. You could arbitrarily choose one of the two products. Or if we asked you for what the theoretical yield would be for one of the two products, like the nickel phosphate, you could pick that as a product. And you would take each one of those reagents and work out how much product you would make in grams. And then you would select the one that has the lowest amount. So that shows you how you can use stoichiometry to do both a volumetric analysis problem, which is what we show here, or it could feed into any one of the problems that we had in Chapter 3.